Hi everybody. So in this video, we're going to look at how to use the chi-square test for homogeneity. Now, the terms could be a little bit off-putting, but just like in science, a homogeneous mixture is a mixture that is mixed thoroughly and equivalently all throughout. So when we're doing a chi-square test for homogeneity, we're going to be looking at several groups or populations and seeing if the distribution of a variable is the same throughout each of those groups or populations. So before we dive into that, this kind of connects to our study of statistics from the first 3 chapters. So I have a warm-up question up here that I'd like you to pause this video and try, kind of refresh your memory as we're getting ready for that AP exam. So, does background music influence what customers buy? Market researchers suspect that background music may affect the mood and buying behavior of customers. So one study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, or some other entree. The data from this experiment is summarized in the two-way table below. I would like you to calculate the conditional distribution in proportions of the entree ordered for each treatment. Go ahead and pause this video now and calculate that. Okay, so welcome back. So when you're calculating a conditional distribution, what you're calculating the distribution of is what you're allowing to vary. So here we're calculating the distribution of entree ordered. So I'm going to allow the different entrees to vary for each of my treatments. So I'm going to think of each of these 3 groups as its own separate kind of category. And then within that category, I want to look at the distribution as a proportion. So 30 out of the 84 total ordered French food where no music was playing. 39 out of the 75 total ordered French when French music was playing. And you could go so on and so on for each of these. As I go through each of my distributions, within each of those categories, the sum of the percents should add up to 100, as those constitute the total percentage of all of the values. So here we can take a look at these. So if I'm looking at entree ordered when no music was playing, as I mentioned, I got 30 out of 84. For Italian, it's 11 out of 84. And for other, it's 43 out of 84. That gives me each of those percentages. Now, since I want to do this for all of my categories, it's going to take up a lot of space to write this in. So my recommendation for you, if you have this question on the AP exam, is to just write those proportions into the table as you calculate them. And then for this question, just say see above. And an AP reader totally knows what that is. In fact, they expect it. So here are my 3 different conditional distributions of entree ordered for each type of music. Again, as I mentioned, the sum of the distribution in each of those categories is 100% because it's making up 3 individual totals. So what I'd like you to do now, as long as you had your percentages correct, is to make an appropriate graph to compare these conditional distributions. Again, you can pause this video to construct that graph. Okay, so there are a few different ways you can answer this question, a few different kind of graphs that you can make. So the 2 that you may have instinctively gone to is a side-by-side bar graph or 3 segmented bar graphs. So those are perfectly valid. In fact, those would be my preference. If you didn't recall this unit as well, you may have just done 3 separate bar graphs, which is what I've done here. And that's also totally acceptable. So notice that I'm just transcribing those conditional distributions. And the reason I'm using the conditional distributions and not the actual frequency is because I have a different total number of subjects for each of those treatments. So if I want to make direct comparisons, I have to do it percenty. So I can see I have 3 separate distributions here. Each of them have the same categorical variable, entree ordered, and they're both all done in relative frequency. And I'm just looking at 3 separate distributions. So what I'd like you to do now is to write a few sentences comparing these distributions just to see what stands out to you using the techniques that, again, we covered earlier this year. So go ahead and pause this video one more time and fill that in. Okie dokes. So some things that may have stood out to you is that I noticed that there definitely seems to be an association between the music that's playing and the entrees that were ordered. The reason that I say that is that these distributions are not the same. When different music is playing, that seems to have an effect, or it seems to be associated with, at the very least, a change in order preference of different entrees. And I want to explain that. And then I also want to kind of go further and explain what differences I'm specifically seeing statistically that make me believe that. So here's a model example of a full description of what I'm kind of looking at in these values. So the type of entree that customers buy seems to differ considerably across the different music treatments. Orders of Italian were very, very low when French music was playing. I can see that when French music is playing, almost no Italian entrees were ordered, whereas there seems to be a considerable increase in the number of French entrees that was ordered when French music was playing. Similarly, if I look at some of the other treatments, when Italian music is playing, there seems to be an increase in the percentage of Italian orders as compared to French or none. And when no music is playing, it's just 13.1%. So there's definitely seems to be an influence in the music. French entrees seem popular in this restaurant regardless of what music is playing. Again, if I look at all three distributions, French is more than 30% in each of these. In fact, it's very close to half, or almost 40% every time. Additionally, as they ordered frequently under all the conditions. Yeah, so there was also, for all three treatments, the percent of other entrees ordered was similar. So there doesn't seem to be a change in the other entrees. The main change seems to be between Italian and French across all of these distributions. So those are all the things that you should pick up from looking at this graph. So then the question is, and this is what we're going to answer in this video, is this difference, this variation in the percentage of entrees ordered for each of these types of music statistically significant? Meaning, is there evidence that these differences could not have happened by chance alone? And that's what we want to answer. So that's the new component. So do these data provide statistically significant results to support the following hypothesis? So essentially, is there no difference in the true distribution of entrees? Again, we were just looking at our sample from our experiment. So there's some sampling variability. So is there really no difference in the distributions and we're just observing our differences by chance alone? That's the null hypothesis. And the alternate hypothesis is that there is a difference in the distributions depending on the type of music that you're listening to. So these hypotheses are the foundation of this chi-square test for homogeneity. And we essentially use this test anytime we have multiple populations or treatment groups, and we're looking at the distribution of a single variable. In this case, my single categorical variable is type of entree ordered. Okay? And my populations, or my treatment groups, are the three kinds of music that the individuals are being subjected to. So that's the general chi-square test for homogeneity. Multiple populations, one categorical variable. Is this distribution of the categorical variable the same or different across those treatment groups? So that's what we're looking at. Okey-dokes. So the chi-square test for homogeneity looks very similar in terms of conditions to the chi-square goodness of fit test that we've already studied. Again, I want things to come from random samples or from a randomized experiment. If I'm sampling without replacement, I need each sample to be less than 10% of the population. And then I have my large counts condition, which is all of the expected counts need to be at least 5. The thing that differs is where the expected counts come from. So there is a formula that I have up here. When you have things arranged in a two-way table like we did just a moment ago, you can calculate the expected counts by taking the row total times the column total and divide that by the table total. So just a moment, I'll explain where that formula is coming from so that you have kind of an intuitive sense of why this is the way we're going. And I do want to note that this formula is not on the AP reference sheet, so it is something that you will have to memorize. But again, we're going to go over where that formula comes from as we counted the calculations, so hopefully it makes some intuitive sense. So let's look at it in the context of this example. So here are my observed counts. Again, this is the same two-way table. I've just kind of made it a little bit smaller and easier to follow. And I want to check that the conditions are met. So first is the random condition. This is a randomized experiment. We were told that subjects were randomly assigned to treatments at the very beginning. So I've met the random condition. And because it's an experiment and I'm not sampling without replacement, I don't have to do the 10% condition. So now I have to do the large counts. And that's where this formula is going to come in. So if I want to calculate an expected count, like suppose I want to calculate the expected count for French under none. So this first cell, entree ordered French and none, and I want that expected count. So my observed count in that category is 30. The expected count is the row total, which is 84, times the column total, which is 99, divided by the total, which is all of the subjects who took part in this experiment, which is 243. And I can go over to my calculator over here, do 84 times 99, and divide that by 243. That gives me 34.2. 34.22, and that is the expected count that corresponds to none with French. And I could go through and repeat that exact same process for any of my cells. So suppose I wanted what the French-Italian one would be. So I could take 75, multiply that with 31, row total times column total, divided by total. And I get 75 times 31 divided by 243. So I should get 9.56. And if I reveal that so I can see if that's correct, I get 9.567, which rounds to 9.57. So that is the correct value. I can do that for each of these and kind of go through, and I'll get all of the expected counts using that formula. So then the question is then, why? Why does this formula work? How is this giving me my expected counts? And all of that has to do with the null hypothesis. The null hypothesis assumed that there is no difference in the distributions across the different treatment groups. That's the assumption that we're starting with. So if that's true, then these different categories don't really make any difference at all. And it's all just one big sample of this overall distribution. So if that's the overall distribution, there should be an overall probability of ordering a French entree of 99 out of 243. So that's the marginal distribution for French entrees. If that's true, if that's the probability of ordering a French entree, and there were 84 people who didn't listen to music, I'd expect 84 times the 99 out of the 243, that proportion of the 84 to have ordered a French entree. And that's where this row total, the 84 times the column total divided by the total is coming from. It's essentially the sample size, n, times 99 out of 243, which is p. And that's NP is where all of the expected success is. That's how we've computed it all year. Number of observations times the probability of a success. So it's that same NP, but when we're looking at it across all these values, and we're making that assumption that there should be no difference in among different types of music, I'm looking at just the overall totals, because these different subcategories should not make a difference. So that's where that formula comes from. So again, going back to my conditions, large counts, my smallest expected count is 9.57. So all my expected counts are at least 5. So I've met the conditions to use the chi-square test for homogeneity. So we're good on all fronts. Next, we have to do the computation. And this is the part that can get kind of tedious. So what's nice is that the chi-squared statistic never changes. It's the same formula for goodness of fit test, for chi-square test for homogeneity, or chi-square test for association, which is the next test that we'll look at. The one thing that does change for the general chi-square test is the degrees of freedom. It's number of rows minus 1, number of columns minus 1. That's how the degrees of freedom works. This is essentially there's a reasoning behind this, and we'll look at that when we next meet in class as to why these degrees of freedom. But if I wanted to check what the degrees of freedom were for this particular example, I'm just going to do number of rows, which is 3, number of columns, which is 3. So 3 minus 1 times 3 minus 1 was going to give me 4 degrees of freedom. So that's where the degrees of freedom comes from for the chi-square test. Again, that is not on the reference table. So that is something that you would have to keep in mind. It's essentially kind of an added number of population or number of different groups minus 1, and then number of variables minus 1. So that's why it's kind of similar to the degrees of freedom for the goodness of fit test. It's just now that I have more than one population. So let's actually go through and compute this chi-square statistic, keeping that information in mind. I'll show you how to use your calculator and also table C if you are going to do this using just the reference table. Okay. So to compute the chi-square statistic, again, it's observed counts minus expected counts over expected with the numerator squared. So my observed count is 30, my first one. My corresponding expected count is 34. So I'm going to do 30 minus 34.22 squared over 34.22. And I'm going to continue doing that for each of the corresponding variables. So I'll look next at 39 and its corresponding value, 30.56. Take that difference, square it, divided by the expected. And I'll keep doing that all the way until, for every single one of these, all the way until I get to 35 and 39. And if I do that computation, it's very tedious. You have to go through each one of them by hand in the calculator, computing them to get the sum. And if you do that in this case, you should get 18.279. This is why Tony Stark really hates the chi-square test, because it is super tedious and computationally belabored. As we mentioned before, degrees of freedom is 4. So now comes, how do I come up with the p-value? So there is a way to do it very precisely with your calculator. So you can go to second distribution and then scroll down to chi-square CDF. And I can go from this chi-square statistic, 18.279, up to some absurdly large value, because it should continue infinitely to the tail, and then comma the degrees of freedom, which is 4. If you want directions for this, it is in your textbook, and I'll mention that in just a minute. So I get a p-value of about 0.0001. So there's my p-value. If you were doing this using the reference table, we'd have to estimate the p-value, because the reference table doesn't give me a value as precise as the calculator will. So to use the reference table, basically this is the table C in the reference sheet. You can go to 4 degrees of freedom, which is the 4th column, and try to find your chi-square statistic. So the closest one to it is going to be 18.47. And this is why I say it's approximate, because it's not really close. So our statistic is somewhere between these two values, which is going to give me a p-value somewhere between 0.025 and 0.001. Since we're closer to 18, it's going to give me something closer to 0.001, but irregardless, these are both less than a significance level of 5% or even 1%. So no matter what, we're going to determine that it's statistically significant. So the reference table is not as good as getting a specific p-value, but you can use it to estimate. Just locate your degrees of freedom and then find a test statistic that's closest to the one you have. That's going to give you the approximate p-value up at the top. Okay, so I'm going to come back to my question now that we have all of the values. So that's the do part of this. And then finally, I'm going to make a conclusion. So as I mentioned, that p-value is less than any reasonable alpha level. So if we're using a 5% significance level, we're going to reject the null hypothesis. So what that means in context for this is that we're going to conclude that we have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is playing. So there is definitely a difference in the distributions depending on the treatment. Okay, so that's the chi-square test. So we definitely have our results, and that's great. So if I am the owner of this restaurant, though, I'm like, great, listening to music changes preferences. Wonderful. How does that help me as a business owner? So something that often happens after a chi-square test is performed is a follow-up analysis to see exactly where the strongest component of that difference is coming from. So which of these things is causing this strong difference in the distributions among the populations? So to do a follow-up analysis, we have to look at each of the individual contributions to the chi-square statistic. Now this is, if you had a mini tab, which the AP exam sometimes uses, this actually reports all of the components. So this first component is the observed count. The second component here is the expected count. And then this third component is called the contribution, and that is the observed minus expected squared divided by expected. So that's the part of the chi-square statistic that is called the contribution. And if I sum all of those contributions together, if I add all of those individual contributions up, I get this total chi-square statistic. So the thing that stands out to me is that when I'm looking at these, the largest parts are this one, which is 7.672, and this one, which is 6.404. And if I notice what's happening here, this value is much less than expected, and this value is much more than expected. So this is where the biggest difference in my distributions is occurring. And it looks like ordering when French music is playing and when Italian music is playing, it's the change in this order. So I actually don't remember what that second column was, so I'm going to go back a second. So that's Italian. So it's ordering Italian. So when Italian music is playing, there is, when French music is playing, there's far less people ordering Italian entrees than would be expected. And when Italian music is playing, there are far more people playing Italian music than I would expect. So that tells me that the Italian entree is the one that is most susceptible to the music that is playing. So that's the biggest one. So my takeaway after looking at this is that we could see that of those two components alone, when I put them together, the 7 and the 6 make up 77% of the chi-square statistic. It's almost all of it. It's 3/4 of it. So my conclusion is that orders of Italian entrees are the ones that are affected by Italian and French music the most strongly. So if I'm the business owner and I'm looking at this follow-up analysis and I have a lot of leftover Italian entrees that I need to move, this follow-up analysis tells me that I should pop on some Italian music, and that's going to help me move those entrees a little bit quicker. It's less so with the French entrees, and the other entrees don't seem to be really that affected at all. If you look at other, those contributions are minimal. And then there is a slight increase. So that we expect 30.5, but we had 39. For ordering French entrees when French music was playing. So there is a slight association for French, but the strongest is with the Italian. So that's where that follow-up analysis can be helpful. Essentially what I'm doing is I'm finding the largest contributions to the chi-square statistic, and I'm trying to make meaning of that. So I have more Italian orders when Italian music is playing and less Italian orders when French music is playing, and those are the two biggest contributors here. Okay, one last thing that I want to mention before we close this video, and that's how to perform a chi-square test using your calculator. So here's another question. This is data on drinking behaviors for independently chosen random samples of male and female students. And this comes from an article, Relationship of Drinking Behaviors to Alcohol and Cigarette Use by College Students, which was published in 1992. So does there appear to be a difference with respect to gender, or a difference with respect to drinking behaviors by gender? So this is a chi-square test for homogeneity. I have two different samples that I'm sampling from. I have a sample of men and a sample of women, so two separate samples, and I'm trying to see if there's a difference in the distribution of drinking behavior for each of those sampled genders. So I'm going to start by assuming there is no difference in the distribution of drinking behaviors between genders, and then I will have an alternate that there is a difference in the drinking behavior. So those are my hypotheses. I'm not going to write out the conditions, but if we check the conditions, I have two independent random samples. It was stated independently chosen random samples. So I have the random condition, 10% So this is of college students, so randomly selected college students. And if I look at the total of there, it's reasonable to believe there's more than 9,800 male college students in existence and more than 10,360 female college students in existence. So the 10% condition is satisfied for both samples. And then the expected counts condition. So as I said, I'm going to show you how to do this using a calculator. So it's actually going to save me time from calculating all of those expected counts by hand. The one caveat is you have to understand how to use matrices. So I'm going to pull up my calculator. I'm going to make it a little bit bigger so that you can see it a little bit better. The way we run a chi-square test on the calculator is I first have to go to matrix. And matrix is the second key of the X inverse button. So when you go to matrix, you're going to scroll over to edit and hit enter, and it's going to allow you to create a matrix of whatever size you want. So you can change the sizes by changing the two numbers at the top. Like for example, if I change this to a 3 and hit enter, it's going to add a third column in. So matrices are rows by columns. So I need a 4x2 matrix to enter this data table. And all I'm going to do is enter the actual raw data. I don't have to enter the column totals because the calculator will compute that for me once I run the test. So I'm going to transcribe all the data as seen in this two-way table. And once that's all entered, I'm going to quit and I'm going to go to stat tests. Okay, so once I'm at stat tests, I'm going to scroll through the list. It's easy just to scroll up from the bottom, and I'm going to find the general chi-square test. So not the goodness of fit, because this is a chi-square test for homogeneity. So I need a general chi-square test, option C. It says observed, it says expected, and it says calculate. So as I mentioned, you don't have to calculate the expected. It's actually going to calculate it for you. So I have typed my observed into matrix A, and then it says matrix B as expected, and I'm just going to ignore that for now, and I'm going to go down here and click calculate, and it will calculate. It'll do all the do. I get the chi-square statistic, the p-value, and the degrees of freedom all reported to me. So I'm going to drag all of that over to my workspace here, and I got those values. So assuming the conditions are met, that would be the do part. So the reason I'm doing this out of order is one of the benefits of this chi-square test is if I go back to the matrix menu, so I'm going to clear, hit second, matrix, and I'm going to highlight matrix B. Sorry, I'm going to scroll over to edit, and I'm going to highlight matrix B, and I'm going to hit enter. And this matrix B is now populated with all of the expected counts. The computer or the calculator has computed them and stored them for me. So I'm going to drag that over to my workspace as well. So here are the expected counts. And if this was an AP exam or an AP question, the thing that I would do is because obviously you can't drag your computer screen, is I would transcribe these expected counts. And what I would do is add a little, I add a little thing that says EXP for expected in parentheses, and I would just throw those expected counts right in next to all of the observed counts so that I can have them in a place which kind of makes it easier for me to see them. And you could fill all of those expected counts in here. So then when you go to check the condition, when you're checking the large counts condition, if this is an AP exam, you could say all counts greater than 5, and then just say see table. So that would be sufficient work on an AP exam so that an AP reader knows that you have written all the expected counts in. It's written right into a column that already existed, so it saves you time from creating a column, and it shows that you've checked the conditions. My smallest expected count is 38. That's bigger than 5, so I definitely meet all the conditions for this test. So that's using the calculator. From here, also the reason I have this question is that if you ever get one of these weird p-values, this e to the negative 21 is calculator shorthand for times 10 to the negative 21st power. So what that tells me about this p-value is that it's 0.000000 20 times 86. So it's essentially 0. The p-value is essentially 0. So that's a common thing that the AP exam will do, is give you a p-value that's essentially 0, so that any reasonable significance level, I'm going to find these results to be statistically significant. So because my p-value is less than alpha, my results are statistically significant. We have sufficient evidence, or we're going to reject the null hypothesis, and we have sufficient evidence to suggest that there is a difference in the distribution of drinking behavior between genders of college-age students. So that's using the calculator. All of that I've just gone over is actually available to you in the textbook. You can look on page 787 and 788 for a description of how to, step-by-step, how to use the calculator to run a chi-square goodness of fit test using matrices. It's a real time saver if you're tech savvy for figuring that out. But if you are not that comfortable with the calculator, again, you can just compute it out by hand the way we did for the last example. Dokes. So we will open our next class with a warm-up question, the next question that's in this packet from this chi-square test, and we'll go over any questions that you had about this topic. So until then, I'll see you soon. Take care.